Start the recording, guys. Let's do research. Let's do research because I want to have research done by the end of today. Let's do it. Let's do it because I'm very positive. Today is good. Today is good. Let's go over those papers we want to read. Yes. Okay. Let's go. Where are they? Let me close some stuff. Learning MMNL, we have that paper, which is great. But I don't think we need it actually at this time. It's about the algorithm to implement learning mixed multinomial logic models. Okay, last night I also looked at variations of MNL which allow mixed and which allow for multiple choice. And so we had this paper and we had also another thesis or something. The evolution of click-based MNL. Let's go click-based MNL also. Is this the, yes, this is the thesis. No, there was one that had a... Yeah, okay, so learning mixed multinomial logic models is by... it's from MIT. It is... It is actually the IDSS, David Simchi-Levy. And learning mixed multinomial. What year is it, by the way? Year... Yusuf Marzouk was Dimitri's supervisor. Yeah, Dimitris is now in SF. MIT Center for... I don't know why Dimitris didn't go to Miami instead of SF. Alright. Multinomial logic model is widely used to predict the probabilities of different outcomes. However, the standard MNL model suffers from several issues, including but not limited to the heterogeneous population. This is why we are here too. Restricted, independent of irrelevant alternative assumption, insufficient model capacities. We read all of this last night. Other limitations of a standard MLL model, including lifting the IAA assumption. first inspired by the recent work in Gaussian mixture models, topic one. Polynomial learnability of, so it's about how efficient or time consuming is MMNL is. Theoretical point of view, which these are good, but I think they are at this level that we are right now. This is too much detail to get into the algorithm. We first want to know what is the main thing, what is the main approach, and then you can say, all right, this algorithm converges better. So, wow, that's interesting. Chapter 2 sounds interesting because it studies the polynomial learnability of MMNL models with a general k number of mixtures. Okay, for me, learnability, not important. It seems they are learnable, and what is important for me is the k number of mixture. What does that mean? The current result that only apply to we are not even fixated on MNL right now. We are like, we have topic modeling, we have MNL, which one we should go? I'm saying this stuff because when I get to chapter 2, I want to remind myself not get into details, because I tend to do this kind of. Actually, being TA this semester really helped me, because I was reading papers from different venues or fields of research, and I couldn't get into the detail of them. I wouldn't understand. I was reading papers from biology, so I had to abstract away a lot of things. I think that was really good. Being TA is actually a very good experience. Or maybe this is this course. It was about research, and I was also motivated that, okay, I had this PhD experience, now I can help people who wanna do research. I can be with them and help them if they need me. So share my experience. So I think it was a good course. It was not just being TA. The course was really amazing. So it's not and I learned a lot. So chapter 3 is about Frank Wolf. Always look at the abstract first. Honestly, I got much better at reading papers. Thanks to Dina, mainly Dina. And tracing also. So when I'm reading this book, I want to know what is the data set, how it looks like. So chapter 1, introduction, mixed MNL formulation, multinomial logic, random utility models, mixed multinomial logic. We already went over them, literature review and overview. What is the difference of review and overview? Review or review? All right, I don't want to get involved. We are chatting with Amin. I don't want to get involved now. All right, this is it. And then I want to say, why am I distracting myself? All right, why did I go to my phone? I went to my phone because I wanted to say we have mixed multinomial logic and multinomial logic and random. Fuck. Oh, review and overview. Okay, what is the difference of review and overview? ChatGPT. What is the difference of review and overview?
A review typically involves a critical evaluation or assessment of something, such as a product, book, movie, or service. It usually includes the reviewer's opinions, detailed analysis, and a recommendation or rating. An overview, on the other hand, is a general summary or broad description of a subject. It covers the main points or features without going into a detailed critique or providing personal opinions.
But they share a lot of things because you in both of them you need to view them.
That's a fun way to look at it.
Fuck off. Don't laugh at me. Alright, go ahead.
Got it. No worries. So, while both a review and an overview involve examining something, a review focuses on critical assessment and personal opinions, often with a recommendation or judgment. An overview, in contrast, provides a broad summary or general outline without going into detailed evaluation or critique.
Alright, shut up, bitch. I don't like when he laughs at me. Alright, then chapter 2 is about problem formulation, identifiability. Right? So what is identify? If we have, okay, I don't know identifiability, if it is the same identifiability we are talking about, that we need multiple clicks or one click is enough, it's about something else. Let's not the same words like trick us. Mathematical and statistical tools, semi-algebraic set, and Tarski's silent. That sounds like very cool stuff. Whenever I hear Tarski, I'm like, what the fuck? Methods of moments, and then polynomial learnability. So it's about the efficiency of algorithm. It's not about is it learnable or not. The great search algorithm, main results, learning MMNL with provable guarantees, a data-driven approach. Well, these are interesting problem. Oh, problem formulation is in chapter 3. Can I open a copy of this work and go to chapter 3 right away? Stochastic subregion Frank-Wolf algorithm. Let's do that. Fuck that. I don't want to go further. Yeah, how menu, open a new window, new window, yes. No, what the fuck happened? Yeah, okay. We'll put it here, yeah. Okay. And now I go chapter 3 to learn what is the problem formulation, page 50. Okay, learning MMNL with provable guarantees, data-driven approach, that's bullshit. This chapter we will stochastic subregion Frank-Wolf from a data-driven perspective while still providing provable guarantees to this. between this and chapter 2 lies in that this chapter makes assumption on the data structure and is a more practical. Okay, I want to know data structure. And is a more practical method that can be used in real world application in section 3.1. We will formalize the learning problem and identify some key assumptions in our setting. Section 3.2, we will describe the original Frank Wolf approach, analyze underlying issues, algorithm. We will formalize the learning problem, identify some key assumptions in our setting. We'll describe the original framework approach, analyze its underlying issues, and present our framework. This is of two parts, the SSR-FW algorithm itself and a Q construction algorithm, whose output will be taken as input to the framework finally. Okay, fuck your sections. I want to see the description of data. Alright, different from the previous chapter, we will assume using the standard MMNL notation as introduced in chapter 1, recall setting where the decision makers and to choose among a set of M items. Alright, you have M items instead of N items, where each alternative J is associated with a feature vector Zj. So in ChatGPT it was X, now it's Z. And assume the population is modeled by an MNL model consisted of, is it an MNL model or a MNL model? Alright, K individual MNL mixture components, K individual, what is, oh okay, I want to know what K is also. Which decision makers within each component exhibit the same logic parameter. That's actually what we want. Alright, so furthermore, we will focus on a linear utility function with respect to the observed attributes. I'll like this is BKJ is beta KT. In beta K is represent the decision maker's taste. This is about the type and the thing we were talking about. So now I want to open a new window as well and go see what are these types and where is this mixed multinomial logic. No, not mixed. The mixture. Where is the mixture coming? Mixed array. Mixture type, numerical experiment and case studies, data generation. Oh, it's chapter 4. Wow. In the case, MNL are consists of K individual MNL components. This is sometimes referred to as latent class model. Alright, I like that. We can, where we want to model the choice of behavior of a decision maker, but which contains K different types. I love that. Choice preference when facing the set of options. Psychology and marketing. So mixed MNL is the way to go actually. This is a good paper, honestly, this is a good paper. Actually, it has not. If you want to decide to use MNL models, we can use this we can learn a lot from this instead of thinking. That can address the issue in existing variation, relaxing the assumption on model search and providing desirable theoretical parting particular interest in the provable convergence of the estimators. We want the algorithm to generate the estimates alpha k hat such that epsilon greater than 0 delta. After 2 studies polynomial learnability with a general k number of mixtures, this whole word relates. Alright. So case types. Okay, now we have problem formulation. So problem formulation, chapter 2 and chapter 3 are different. We have 2 sections. We introduce a slightly different notation in this chapter to be consistent with the past work done in the theoretical learning setting, specifically considering p theta, the family of KMNL model for a set of M alternative denoted by M, 1 to M, small m this time. We also refer to this setting as KMNL models under an M item universe. We can also think of p theta as M size vectors where J's element is a probability of choosing alternative. We can also think of p theta as an M size vector. We have M items where the J's element in p theta is the probability of choosing alternative J. P theta is parameterized by theta in Rkm plus 1. We can write theta is Rk, theta mk minus 1, which each theta from M are a distribution over delta m minus 1, where delta n minus 1, theta 1, and sum to 1. So it is m. So this is the paper. If there is something about using MNL, it is the paper. All right. Alternative J given the entire alternative mixture weight. What is the mixture weight? I want to know what is the mixture here. Model for given a slate as in we let theta s as a parameter subspace of theta. I didn't get how users selection model is. Then they go to identifiability, conditions, and is it logic? Fucking truth table for logic. But I didn't get how they generate data. All right, let's go to chapter 3 also. And then we finally have this, and then there are these probabilities and aggregated counterpart for entire population. model assumption, QKJ, QK prime J. You know what? I don't want to think about the consequences of my actions. Honestly, I want to live simply. Yeah, I'm saying the right thing, and they say you need to care. Oh, why? What? What are the consequences? FNG became a association to different traces, probably. FX, like, oh, you're siding with them, siding with those. Fuck that. Fuck all of you. I want to do the thing that I believe is right. I don't care if wrong people are doing it or not. I need to look at it as a whole. I think me and Amin should have it won't be a podcast, it would be a fight, debate, or whatever it is. GX, J1, 2KX. What are these, honestly? Okay. Data assumption, beautiful, alright. We will assume to work with repeated choice data. What does that? Oh, that's interesting. Such as consumer panel or survey data. This is a reasonable assumption in many real-world scenarios. For instance, this in particular, we assume the data consists of historical choice decision from the target population of size n for each time period t equal 1 to t. We consider decision maker i's choice xit, IID random variables drawn from a categorical distribution with parameter qk. If the decision maker is of type k, this means the support of xi is m. To be the real, I think that's the part we are really care about. What that was one of our main questions as well. That okay, we have this multinomial logic, we have variations that user is allowed to have multiple choice, and then we have our topic modeling, we have our cascade model. How is our real data? Because we still don't have the data yet. So if you want to simulate a data set, how should it look like? With the probability if the decision maker is of type k, this means the support of xi is m, not xit be the real, and yit we have on hot encoding vector of xit. Finally, we state our main learning objective to minimize the difference between the observed from data theoretical aggregated choice probability vector as follows. In notation, we omit the observation data permits. For the loss term, we can expand equation 3.1 with the actual set of parameters and stochastic subregion Frank-Wolf algorithm. How do you generate your data? That's so simple, but you don't tell me. Provable, and then we wanna have what page is it? Problem formulation with provable guarantees. Yeah, 49. Oh, it's here actually. Alright. Alright, what else is interesting in this paper? Interesting. Section original, I don't want to get into Frank Wolf now. Numerical experiments and case studies. Simulation and data generation. Every section has a data generation, every chapter. Four is page 79. Simulation studies data generation. We generate the data using the following set of hyperparameters. Choice size M is 10, which is the number of items with an offset option 0. Population size is 2000. Number of mixtures k equal 5. Types. Mixture means type. If only A, B, C, D, E. Feature vector dimensionality is 10. What are they? For us, it is the relevance. We can may say price, and then we add position. Then that's it. Time spent on timelines, time periods, t equals 5 to 300 with increment of 5. What is time? Number of seats, L75, cardinality of Q. Note that we also include the offset option to allow the possibility of choosing nothing from the option set. This is a more realistic case in many real-world applications. Different options and preference vectors, beta keys are randomly generated. The wrong alpha keys are randomly generated such that minimum mixture, sample purity. So here they have this notion of time that is not present in our work. And through that they let like repeated choice. Okay, they have a data curation. There were 6 different categories, including yogurt, cereal, and snack, candy, soft drinks, and pet. We then provide some summary statistics in table. Case study, categories, and data information. Pet food, candy, cereal, snack, soft drinks. Experiment setup, results. This is a good paper, but I don't want to dive deep into it. Dive deep or dive deeply? Alright, and grammar. Both of them are correct. DiveDB is more common in informal or figurative context. American English, it's often used as an idiom, meaning to explore something thoroughly. Dive deeply sounds a bit more formal or literal and is used more often. Physical action or when you to a more traditional adverbial form. Okay, so dive deep is correct. Perfect. Questioning myself. I don't feel like diving deep inside this fucking paper right now. And then we have another paper called Learnability. Learned mixed. Oh. This is the same. Oh, okay. Click-based MNL. The click-based MNL model, a novel framework for modeling data in assortment optimization. And we introduced the click-based MNL choice. It is warm. I need to turn this. No one doesn't spend some time. Click-based MNL choice model, a novel framework for capturing customer purchasing decision in e-commerce setting. We augment the classical multinomial logic choice model with the assumption that customers only consider the items they have clicked on before they proceed to compare their random utilities. So it's like a Nagin's work, huh? We propose a simple estimate. It's two stages. We propose a simple estimation framework that leverages click-stream data. Click-stream data. What does that mean? And machine learning classification algorithms. We study the resulting assortment optimization problem where the objective is to select a subset of products. Objective is to select a subset of products. Okay, it is interesting. Subset, not an item, not one member of the product, not an element, but the whole subset made available for purchase to maximize the expected revenue. Our main algorithm contribution comes in the form of a polynomial time approximation scheme. So about these algorithms, they are very important that we polynomial, fuck polynomials. For this problem, showing that the optimal expected revenue, I'm not gonna spend my time on polynomial of both here. I'm gonna find something more important. Expected revenue can be efficiently approached within any degree of accuracy. In the course of establishing these results, I'm not saying, you know what I'm gonna do is, I'm gonna say, running this algorithm takes 1 minute. That's what I'm gonna say. Fuck polynomial, who cares about polynomial? Can be efficiently approached within any degree of accuracy. In the course of establishing these results, we developed novel technical ideas, including enumeration schemes, and stochastic inequalities, which may be of broader interest. Should you add it in your abstract? I say no. Using data acquired, I don't like that line actually. Either say this is a big result theorem we have, or saying it's such a vague general way, I don't like. Using data acquired in collaboration with Alibaba, we fit click-based MNL and mixed MNL model. It's also about mixed MNL to historical sales and click data in a setting where the online platforms must present customized 6 product displays. Okay, this is 6. We show that our approach significantly outperforms the mixed MNL model in terms of out-of-sample predictive accuracy, and the computational cost of its estimation process is smaller by an order of magnitude. That's interesting. So multinomial Majid consideration set, it's about consideration set, it's not just one choice. And then click stream data, that's interesting. Approximation algorithm. So they had access to Alibaba's data. Assortment optimization is a fundamental online platforms where the set of products can be seamlessly varied and personalized at essential no cost. Existing prediction models and decision support tools in this context generally take advantage of historical transaction data to infer customers' preference. Now they're saying we don't want to do that. As each purchase, look, these 2 papers are really important, I can say that. They are vibing. As each purchase transaction reveals a choice made by corresponding customers amongst the available products. As each purchase transaction reveals a choice given this probabilistic prior about customer preferences, the selection of an assortment to maximize expected revenue can be framed as a combinatorial optimization problem. Received a great deal of attention in the operation research and revenue management literature, as further elaborated in section 3.1.3. In recent years, online platforms increasingly collect data of operation is all about surface. Alright, in recent years, online platforms increasingly collect data about additional form of customer production. There is click stream information. There's research and click behavior, empirical studies in marketing suggest that data is highly valuable to predict customers' purchase, brand loyalty, and churn rates. I love that. Also, Loudon and Traver, for example, by taking into account the path of web page browsers by the user of an online bookseller, Montgomery et al. Show that the accuracy with which they can predict purchase conversion is increased to 40%. These are very nice papers. Up from a mere 7% without integrating this piece of information. Nevertheless, despite marked research interest around discrete choice modeling in the past decade, the marginal value of click stream data in decision-making models remains most. The marginal value of click stream data in decision-making models still remains mostly unquantified in operational settings. Not quantified, alright, value of data, not quantified. Particularly leveraging this data source within the framework of assortment optimization. apparent blind spots for the existing literature from both modeling and... I like the paper, has a nice flow. Overview of our research contributions. Motivated by the state of affairs in the present, preparing taking on perspective of traditional choice models in e-commerce settings by incorporating click signals. Our main modeling idea is to assume that click coincide with the set of alternatives considered by customers during the product screening phase preceding her final choice decision. This point of view leads us to introduce a choice. Fuck, dude, I told you don't distract yourself. No, we don't have any lecture done. The model approach is inspired by the well-established literature around two-stage choice model, which were originally conceived by Derendin. Oh wait, we adapt from the existing literature in viewing the consideration set as being explicitly defined by the click behavior, rather than being an unobserved latent parameter of the choice-making part. So they don't have any latent parameter. What does latent parameter mean? Means type. That's it. Process. Using data from algorithm, we provide empirical evidence that our modeling approach explains customers' choice behavior better than traditional choice models. From a computational standpoint, the random formation of the consideration sets, algorithmic and probabilistic hurdles that necessitate the design of knowledge for the resulting our main technical polynomial time approximation scheme. Our main technical contribution is a polynomial time, proving that the optimal expected revenue approach with any degree of accuracy. So their main technical contribution is a polynomial time approach. Fuck polynomials scheme. It's not fun. I don't care about them. Proving that the optimal expected revenue can be efficiently proved within the degree of accuracy. Alright, I don't give a fuck. And then they also provided a literature review. That's nice. To capture customer heterogeneity. Consideration set. I like that. Alright. consideration set basis or consideration sets are not directly observable. Oh, that's bullshit actually. Oh, I don't like this. Okay. So here they're saying the latent parameter is the considerations that you see a ranking and you say, all right, 2, 3, 4 are interesting, and then I decide between them. So that's actually the latent variable, which is a latent subset. I think it's not helpful to ARMA. Like polynomial time algorithms for certain place either topology. It must be, yeah. Then the iterations are nested. Okay, now look at their model. Click-based MNL modeling approach. Our main modeling idea is to assume that the clicks observed by e-commerce platforms explicitly describe the customer's consideration set, which is also our method. We say, okay, there are multiple clicks. And a key distinctive feature, for example, opening a new tab, feature in relation to the existing literature. Specifically, we define each customer's consideration set precisely as the set of products she has clicked on. So there is nothing hidden about consideration. This assumption is quite natural, considering that customers click on products either to purchase them or to collect additional product-specific information. Following this main assumption, the customer's purchasing process unfolds in a two-step process. In the first step, the customer independently decides whether or not to click on each of the offered products, thereby forming a consideration set. In the second step, the customer makes a purchasing decision by ranking the utilities of the products she has clicked on. Such ranking decisions are captured by a standard MNL choice model. We refer to the resulting choice model as the click-based MNL model, whose dynamics are formalized in section 1.1. This modeling approach has a number of distinct advantages. Oh, then when you click, you go MNL on that part. I'm reading this text, but I don't read it, I don't, my thoughts are somewhere in the first step. Customers independent decide whether, okay. In the second step, the customer makes a purchasing decision by ranking the utility of the product she has clicked on. Such ranking decisions are captured by a standard MNL. So it is first click on some items and then do MNL. It's closer to what we actually. Number of distinct advantages. First click it is massively. Parsimonious. What does parsimonious mean? What happened to India and Pakistan? Jesus. Fuck both of them. I wanna read my paper. Who the fuck? Oh, I don't give a fuck about India and Pakistan creating problem for each other. I'm trying to fix something here. You are trying to cause problem. Fuck both of you. You know. After this many years of being two countries next to each other, you cannot live with each other. Fuck you both. Fuck both of you. You know. That's a good thing. I don't care who started, who finished. So many fucking years. Who's guilty? Fuck both of you. Alright. Standard MNL choice model. We refer to the resulting choice model as click-based MNL. Dynamics are formalized. Whether or not to click on each other, the parameter by framing the resulting choice model as click-based MNL model. Dynamics are formalized in say. What the fuck? Where? Oh, parsimonious. Where is parsimonious? Fucking talk like a human being. I never heard this one. Second, by assuming that the clicks follows independent Bernoulli outcomes, we develop a choice model that is both parsimonious and flexible. Unwilling to spend money or use resources, stingy or frugal. Even parsimonious. Efficient, you could say efficient.
Parsimonious.
Flexible, specifically the property that any potential consideration set occurs with positive likelihood is consistent with the lack of explicit structure and content. Because you have the fucking data. They had to make, don't make fun of them. That in real world certain data such as motherfucker has connection with Alibaba and says la 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 la. For our numerical extent, the property is in sharp contrast with other considerations and basis. Besides in earlier share. If somebody has data, yeah, don't assume this. If you have data, fucking use it. Lastly, the platform's ability to fully observe all click events make the estimation of the model. Section 1.2, the estimation strategy proposed in this paper is very efficient from a computational standpoint, parsimonious, and it can easily take advantage of state-of-the-art machine learning. Okay, we got this. This notion is the assortment optimization problem. Fuck, I don't want to check the news. Is the assortment optimization problem computationally tractable? Assortment optimization problem. Okay. Computationally tractable under the click-based MNL model. Assortment optimization. Fuck. Assortment optimization problem computationally tractable under the click-based MNL model. In particular, can we develop efficient algorithmic methods despite the absence of an explicit combinatorial on the customer's consideration set and ranking preferences. Problem formulation. This formula looks a lot like Nagin's paper. We formally describe the click-based MNL model and formulate its corresponding optimization. We consider a setting where a retailer has access to a collection of 8 items. Each item is associated with a selling price of RI, MNL based preference, weight of WI, and a consideration set probability of lambda I. Inside the selling price, RI, nominal base, preference weight, WI, and a consideration probability. So you have a preference weight and you have a consideration probability. What are these? Like, what are the assortment S? In N, the customer's purchasing decision are made in two steps. By the way, I want to click based on that. I want to check their citation. Yes, that's it. Oh, there is another paper, assortment optimization under the sequential click-based choice model. Let's open it in that. Oh, and this paper extends the click-based multinomial logic model introduced by to explore consumer behavior in some where products are evaluated sequentially according to predetermined order within. Okay, sounds ranking. With this framework, consumers probably click on products during this evaluation process and make an immediate purchase if the currently click products are by their needs. Using data from Expedia, we demonstrate that proposed model exhibits superior predictability than the mixed MNL and click-based MNL models, given the inherent complexity in calculating choice probability within this new model. We are then motivated to propose a fast and efficient algorithm for solving the associated optimization. Our approach leverages a linked random consideration set model where the choice probabilities for exclusively recommending product are consistent with those of examine models for scenarios where the product order is the RCS model is a tight competitive ratio of 0.75 in cases with unknown evaluating orders. The optimal solution from linked towards the RCS model will provide performance guarantees of 0.375 and average case scenarios respectively. Heuristic also provides one to approximate solution. Alright, let's add this paper to our arsenal as well. They actually have something similar to Cascade. Alright, I think I wanna, yeah, dive deep inside these fucking papers. Um, so we wanna know if multiple choice are given or not, and then these are the main questions we have. Alright. Let me take a break. I don't look at my phone. I'm not gonna look at my phone. I promise. Oh no. In the pausing then, I decided to read one paper that I wanna read, and that one is this paper. What is the name of the paper? A comparative study, no assortment optimi, click-based MNL, learning MNL model. Alright, I'm going for click-based MNL. La 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 la, I wanna go for click-based. Let's study this paper. All we are all together. What is this paper saying? Click based MNL. La 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 la. How many citation on Google Scholars? Click based MNL. I forgot to check that. La 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 la. Nina Lula 57. That's not big of a number. I Audan Naiden AMIT Auda assortment under 2021 actually. Very interesting. His most celebrated paper is 2021 assortment optimization under consideration, then choose choice model. Is it the one I already downloaded? Is it the one I already downloaded? Yeah, mine. Sequential click choice model. What area? That's a different. Fuck that, dude. I'm not gonna read two paper. La 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 la. Amir Nouri for how many citation? His papers are amazing. 2NE800. I am just improving my stats and my records. We are. So, guys, I want to say something, and that's the fact that 28 citation is a big number. La 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 la. Let's go la 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 la. Ending project 5 5. Now the click-based MNL introduce a two-stage choice model. A customer consideration set is formed based on the products they click on and then their multinomial model governs their final choice from the subset. Here's a breakdown of the model and its contribution. Key ideas: click-based consideration set. Customers don't consider all display products. Instead, their clicks define what they can see. Then each product has a click probability. Lambda I the consideration set. CS is in CS is formed by including each item I in S independently. Lambda I. Okay. The final choice follows a standard MNL model. Probability choosing I in CS is WI over 1 plus 1 is for nothing, and sigma J in CS WJ. Where WI is the preference weight of item I, and the no purchase probability is no just 1 over this. Sort and optimization objective given to item prices. The goal is to find an assortment S that maximizes expected revenue. RS equals sigma Ri pi of I and S, where pi of I and S equals lambda I, the probability of being purchased, times the probability of being purchased. What? Wait, no. So lambda I expectation given consideration says CSWI over 1 plus W of CS. That is no difficulty as click-based MNL. Alright, I don't get this part. Lambda I. What was lambda I? Oh, okay. Lambda I is the probability of being inside the in the set, consideration set, right? What's new or better? So with probability lambda I, you are in the set. Why don't we have lambda of the whole CS, by the way? I think that should be this base considered. So there are so many details that are not rigorous, observation based, and it's good. We don't want rigor because it just stops us instead of pushing us forward. Observation-based considerations that, unlike other methods that treat considerations as latent or structured, this model uses observable clickstream data. The authors show their model of mixed MNL in a prediction using Alibaba data. Estimating a strategy use MLE to estimate MNL stage and learn by wire. So we used to learn beta. Here we learn lambda I, either by empirical click frequency or machine learning classifiers and I like these parts. Yeah, let's do some machine learning on our data. I don't like. We like a diagram of how these two stages what? How do the data set used in the Klingon paper come from Tmall.com, a large e-commerce platform. I thought it was Alibaba. They're Alibaba. Oh, it is under Alibaba. Here's what we know about the dataset and so dataset description. The data was collected over a 2-week period from the top 10 sellers by traffic on Tmall.com. So it lands on a seller-specific coupon sub-page. 6 products are shown for each customer, and visit the dataset includes the set of products offered, 6 items, the subset of products clicked, so it's a subset of 1 to 6, and well, not really. The final purchase decision, at 25, okay, the second stage, the 25 dimensional feature vector for each product, utility and click models. Is the dataset public? Unfortunately, no, the dataset. So what is the point of it? How is it science if it is not public and reproducible? The dataset is not, how can other people confirm that? The dataset is not publicly available. It was obtained in collaboration with Alibaba and due to confidentiality agreement. How do we know if your data, you are honest about your work? Why should we trust you? Fuck you and your research. Even the seller identities are anonymized. Related resources, you can access the paper's companion. Dude, it is all about commitment assumption in information design. We don't know you. Why should we trust you? I mean, the whole science, by the way, I think that's the problem with the whole science. And I was studying this, I was reading and grading my students' work. They were on bio fields, like studying cancer and stuff like that. And the whole thing, a lot of people say we don't want to do the vaccines and stuff because these scientific researches are not public anymore. I get, like, these companies want to have advantage over their rivals, but at the same time, how can we trust you if we cannot confirm your studies? We don't trust you. It's a trust issue if people do not do vaccine. If you show them that yes, this vaccine works because of these studies, but you don't show your studies, why should we trust you? We have nobody in your company that we can trust. I think it's a trust issue. It's not that people are like flat earthers or do not believe in science, but if you don't show them the science, if you don't let them if you don't let them see what you see and prove that all these steps for themselves, how can they trust you? They cannot trust you. It's a trust issue. Is the dataset public? Unfortunately, no, the dataset is not publicly available. It was obtained, okay. Related resources, you can access the paper's companion material details. I think they are not cited from their SSN. And on the other hand, scientists, they want to do something that is impactful. They need to work with these fucking companies. So they cannot be just on public. There is nothing in public they can work with. And okay, there are a lot of things in public you can work with, but these are also interesting, engaging facts. Like, I'm curious about like this ranking and the effects of it, but there is no public thing that I can access to other than this stuff. And they have their own privacy issues. So the whole thing, everybody has their own point of view, and everybody is right actually. Yeah, if I was a company, I didn't like to share my information. At the same time, if I'm a scientist, I want to do some research. I'm not like, as a person, I have obligation to my sense of curiosity, not only to the whole science world. I want to do something that is interesting to me, not doing something mundane. And other people have their own point of view. If you cannot share your data with me, why should I believe you? You are a complete stranger. We have nothing in common. Why should I trust you? You're wrong all the time. So everybody is right at the same time. You can access the paper's companion material, implementing data from the assistant, but this does not include the data set itself. Being a synthetic version of this data. Can you based on click-based MNL paper, each data point corresponds to a user session. At this time, honestly, I want to do something impactful rather than something that is available to everybody. I want my research has some impact, even if it is for a stupid company. Based on the click-based MNL paper, I had two other papers. They are completely public. I mean, in like every part of it, you can check it yourself. They are reproducible. That's what I mean. It's on the click-based MNL paper. Each data point corresponds to a user session specific. Visit to a coupon page displaying 6 products. The model captures the offer assortment, 6 items shown, the clicked items, subset of the 6. So that's it. That's the problem we have. Science is becoming something that we cannot trust anymore. The click-based, and it's not reproducible. The click items, item purchased, and the feature. Okay, these is stuff I don't care, to be honest. Like, who cares about ranking algorithm? Your machine learning method is reproducible or not. I don't even give a fuck, even if you publish it in Nature or something. But when it comes to vaccine and some stuff like that, that's when it really matters. Here's a simplified example of how one row might look in a structured table format. Example row 1, user visit. Alright, session ID. Nice. I love it. User ID, item feed. What is item feed? Item 1 feed, item 1 click, item 1 purchase, item 2 ID, item 2 feed, and then where is the next? How can I scroll? Item KID, ID of the case, item shown in this session. Alternate the data might be sorted in long format, item ID, user ID, item ID, features checked, clicked, purchased, selection supports both, and then click. Alright, and then let's jump into the paper actually. We are gonna dive not surface, not deep, but medium in the paper. The click-based MNL model, a novel framework for modeling click data in assortment optimization. Dude, I will be exhausted if I want to read it myself, so let's go Speechify.
The click-based MNL model, a novel framework for modeling click data in assortment optimization. Ali Awad, London Business School. We introduce the click-based MNL choice model, a novel framework for capturing customer purchasing decisions in e-commerce settings. We augment the classical multinomial logic choice model with the assumption that customers only consider the items they have clicked on before they proceed to compare their random utilities. We propose a simple estimation framework that leverages clickstream data and machine learning classification algorithms. We study the resulting assortment optimization problem, where the objective is to select a subset of products, made available for purchase, to maximize the expected revenue. Our main algorithmic contribution comes in the form of a polynomial time approximation scheme, PTAS, for this problem, showing that the optimal expected revenue can be efficiently approached within any degree of accuracy. In the course of establishing this result, we develop novel technical ideas, including enumeration schemes and stochastic inequalities, which may be of broader interest. Using data acquired in collaboration with Alibaba, we fit click-based MNL and mixed MNL models to historical sales and click data in a setting where the online platform must present customized 6-product displays to users. We show that our approach significantly outperforms the mixed MNL models in terms of out-of-sample predictive accuracy, and the computational cost of its estimation process is smaller by an order of magnitude. Keywords: multinomial logic model, consideration sets, clickstream data. 1. Introduction. Assortment optimization is a fundamental computational challenge faced by online platforms, where the set of products displayed to customers can be seamlessly varied and personalized at essentially no cost. Existing prediction models and decision support tools in this context generally take advantage of historical transaction data to infer customers' preferences, as each purchase transaction reveals a choice made by the corresponding customer amongst the available product alternatives. Given this probabilistic prior about customer preferences, the selection of an assortment to maximize expected revenue can be framed as a combinatorial optimization problem, which 1. Electronic copy available at https://ssrn.com/abstract=33406220. 2. Has received a great deal of attention in the operations research and revenue management literature, as further elaborated in section 1.3. In recent years, online platforms increasingly collect data about additional forms of customer-product interactions. The primary source of such data is clickstream information, corresponding to the customer's search and click behavior. Empirical studies in the quantitative marketing literature suggest that clickstream data is highly valuable to predict customer purchases, brand loyalty, and churn rates, Lawton and Traver 2013. For example, by taking into account the path of web pages browsed by users of an online bookseller, Montgomery et al. 2004, show that the accuracy with which they can predict purchase conversions is increased to 40%, up from a mere 7% without integrating this piece of information. Nevertheless, despite marked research interest around discrete choice modeling in the past decade, the marginal value of clickstream data in decision-making models still remains mostly unquantified in operational settings. In particular, leveraging these data sources within the framework of the assortment optimization problem is an apparent blind spot of the existing literature, from both modeling and computational standpoints. Overview of our research contributions. Motivated by the state of affairs, the present paper aims to augment the predictive and prescriptive abilities of traditional choice models in e-commerce settings by incorporating click signals. Our main modeling idea is to assume that clicks coincide with the set of alternatives considered by a customer during a product screening phase preceding her final choice decision. This point of view leads us to introduce our motivated by the state of affairs. The present paper aims to augment the predictive and prescriptive abilities of traditional choice models in e-commerce settings by incorporating click signals. Our main modeling idea is to assume that clicks coincide with the set of alternatives considered by a customer during a product screening phase preceding her final choice decision. This point of view leads us to introduce a choice model whose underlying dynamics unfold in 2 sequential stages. In the first stage, the customer forms her consideration set according to the click propensities. Then, in the second stage, she makes a purchasing decision from among the products in this restricted consideration set according to the classical multinomial logic, MNL, choice model. This modeling approach is inspired by the well-established literature in quantitative marketing and operations around two-stage choice models, which were originally conceived by Howard and Sheth, 1969, and by Hauser, 1978, and later empirically validated by numerous works, such as those of Juland, 1979, and Crompton and Ankoma, 1993. We depart from the existing literature in viewing the consideration set as being explicitly defined by the click behavior, rather than being an unobserved latent parameter of the choice-making process. Using data from Alibaba's retail platform, we provide empirical evidence that our modeling approach explains customers' choice behavior significantly better than traditional choice models. From a computational standpoint, the random formation of the consideration sets creates algorithmic and probabilistic hurdles that necessitate the design of novel methodological frameworks for the resulting assortment optimization problem. In this context, our main technical contribution is a polynomial time approximation scheme, proving that the optimal expected revenue can be efficiently approached within any degree of accuracy. Electronic copy available at https://ssrn.com/abstract=33406220. 3. In what follows, we provide a brief review of the most relevant papers on assortment optimization, which sets the stage for a precise description of the modeling approach developed in this paper. A more detailed overview of the related literature is provided in section 1.3. Brief review of existing literature. Starting with the seminal work of Tallery and Van Ryzen, 2004, a growing line of research has explored assortment optimization problems under various choice models and operational constraints. When customer choice is governed by the MNL model, Luce 1959, McFadden 1974, and when there are no restrictions on the set of products to be offered, Tallery and Van Ryzen, 2004, show that there exists an optimal assortment consisting of all products priced above a certain threshold. Subsequent research papers have focused on constrained versions of this problem, extending the breadth of retail scenarios where assortment optimization is readily applicable. Rusmovich and Tung et al. 2010, Sumita et al. 2020. One major limitation of the MNL choice model is its inability to capture customers' heterogeneity. Hence, considerable research efforts have focused on formulating assortment optimization problems with choice models that account for latent customer heterogeneity. For example, a common approach for modeling general substitution patterns is to segment the customers into heterogeneous classes. Since the segment to which each customer belongs is not directly observable, the latter approach gives rise to probabilistic mixture models, such as the extensively studied mixture of MNLs, see, example Rusmovich and Tung et al., 2014, D. Ezer et al., 2014, Feldman and Topaloglu, 2015a. Another popular approach for capturing customers' choice heterogeneity is based on the notion of consideration sets. Most random utility maximization choice models presume that customers consider all offered products before comparing their relative utilities. In reality, however, customers may be led to disregard certain products based on prominent features such as price, ratings, and reviews. For example, they may only consider purchasing products of a certain quality that are priced below some threshold, as in the models considered by Awad et al. 2020, and by Jajabathula and Razmovici and Tung, 2016. Consequently, several recent papers have focused on consideration set-based assortment optimization problems, Davis et al. 2015, Gallego et al. 2020, Awad and Segev 2020, Gallego and Lee 2017. In these settings, the consideration sets are not directly observable, their distribution can only be inferred probabilistically from the final purchasing actions. Moreover, in order to develop polynomial time algorithms for assortment optimization, these studies place additional structural restrictions either on the consideration sets or on the relative rankings over products' utilities. For example, the model of Feldman and Topaloglu, 2018, assumes that the consideration sets are nested. The papers by Hanyan et al. 2012, Awad et al. 2020, and Gallego and Lee, 2017, are all based on the assumption of a unique ranking, meaning that all customers share an overarching ranking over the product's utilities. These modeling electronic copy available at https://ssrn.com/abstract=3340,620. Four assumptions imply that only a very small fraction of all potential consideration sets and rankings occur with positive likelihood during the two-stage choice-making process. Click-based MNL modeling approach. Our main modeling idea is to assume that the clicks observed by e-commerce platforms explicitly describe the customer's consideration sets, a key distinctive feature in relation to the existing literature. Specifically, we define each customer's consideration set precisely as the set of products she has clicked on. This assumption is quite natural, considering that customers click on products either to purchase them or to collect additional product-specific information. Following this main assumption, the customer's purchasing process unfolds in a two-step process. In the first step, the customer independently decides whether or not to click on each of the offered products, thereby forming a consideration set. In the second step, the customer makes a purchasing decision by ranking the utilities of the products she has clicked on. Such ranking decisions are captured via a standard MNL choice model. We refer to the resulting choice model as the click-based MNL model, whose dynamics are formalized in section 1.1. This modeling approach has a number of distinct advantages. First, clickstream data is massively available in e-commerce, thus, our operational use case of click data for designing product recommendation engines is implementable in many e-commerce settings. Second, by assuming that the clicks follow independent Bernoulli outcomes, we develop a choice model that is both parsimonious and flexible. Specifically, the property that any potential consideration set occurs with positive likelihood is consistent with the lack of explicit structure in customers' clicks, as observed in real-world clickstream data such as those provided by Alibaba for our numerical experiments. This property is in sharp contrast with other consideration set-based choice models utilized in earlier literature. Lastly, the platform's ability to fully observe all click events makes the estimation of the model parameters quite straightforward. As explained in section 1.2, the estimation strategy proposed in this paper is very efficient from a computational standpoint, and it can easily take advantage of state-of-the-art machine learning algorithms. Nonetheless, at the core of our model lies the assumption that the observed clicks coincide with the customer's consideration sets. This notion leads to two fundamental research questions. One, how practical is the assumption that customers' consideration sets are described by their clicks? Specifically, How does the predictive performance of the click-based MNL model fare against state-of-the-art choice models on real-world choice data? 2. Is the assortment optimization problem computationally tractable under the click-based MNL model? In particular, can we develop efficient algorithmic methods despite the absence of an explicit combinatorial structure on the customer's consideration sets and ranking preferences? Electronic copy available at https://ssrn.com/abstract=3340. 1.1 Problem formulation. In what follows, we formally describe the click-based MNL model and formulate its corresponding assortment optimization problem. We consider a setting where a retailer has access to a collection of n items. Each item I is associated with the selling price of Ri, an MNL-based preference weight of Wi, and a consideration probability of lambda I.
So we have the price. Omega I, Wi is for the Wi is like e to the beta times features. What is the consideration probability? Is it the probability of observation or the probability of getting click? Lambda.
Given the assortment S subset symbol n, the customer's purchasing decisions are made in 2 steps.
Wow. It just copied lambda I. So it is the probability that the item enters the user's consideration, which is probability of getting a clicked on that item. I in CS given I is in S. What is S? Okay, S is items shown and CS considerations. The assumption is that each item is clicked. Then their data is about just only six fucking items and they're fucking, PTA S. Who cares? Is that each item is clicked independently of others and an item is not clicked for purchase. Okay, independently, so Uh-huh. Exactly, makes sense. Well, lambda I1, lambda I2, lambda I1 minus lambda I4. So, perfect. I love that. Okay, let's continue on reading the paper. I need to take a pause.
One, generating a consideration set. First, a random subset CS subset symbol S is generated by independently picking each item I set membership symbol S with probability lambda I. We refer to CS as the random consideration set induced by the assortment S, whose total weight is denoted by W, CS, equals, I set membership symbol CSWI. 2. Picking from the consideration set. For any given realization of the consideration set CS, a single representative customer makes a purchase from among the subset according to the MNL. WI1 plus W, CS, while the no purchase choice model. Namely, each item I set membership symbol CS is chosen with probability. Option is chosen with the residual probability, 11 plus W, CS. In order to define the expected revenue function, let pi, is, be the probability of picking item I, given that the assortment S is offered.
But where is
Based
the
on the
heterogeneity,
preceding
by the way?
discussion,
Now
this
it's the
purchase
question.
probability
Where is the heterogeneity?
is clearly 0 when I set membership symbol /S. In the more interesting scenario when I set membership symbol S, the latter probability can be written as pi, is, equals PR I set membership symbol CSEWI1 plus W, CS, hashtag I set membership symbol CS dollar equals lambda IEWIS, $1 plus WI plus W, CI, 1. Where the expectation above is taken over the randomness in generating the consideration set CS. With the shorthand notation C is equals CS
CS is
/I.
a random variable.
The
actually.
objective is to identify an assortment S subset symbol and that maximizes the resulting expected revenue R, S, equals, I set membership symbol SRI pi, IS. This assortment optimization formulation is termed the click-based
Where
MNL
is the
assortment problem,
heterogeneity?
for short. Related choice models. It is worth noting that the click-based MNL model can be viewed as a special case of the classical mixed MNL model with exponentially many customer segments. More specifically, in Appendix A, we present a formal description of how any click-based MNL model can be.
The click-based MNL model can be viewed as a special case of classical mixed MNL, with exponentially many customer segments. How? So exponentially comes from the number of subsets we can choose. Formal describe how any click-based MNL model can be converted to an equivalent mixed MNL model. Okay, let's take a look at it. Click-based and the mixed MNL choice model. What do you mean computationally impractical while you have a theoretical proof for it to be exponential? So it's possibly for very small scale. Okay, I like that sentence. K types. Ah, 2 to the 6 is like what? 64. I do a brute force on them. I'm not convinced.
Converted to an equivalent mixed MNL model. Unfortunately, this connection provides little practical value, as the reduction requires specifying a mixed MNL model over two end customer segments, meaning that existing algorithms for the assortment problem under the mixed MNL cannot be efficiently applied to these instances. It is worth observing that even with polynomially many segments, the mixed MNL-based assortment optimization problem is known to be, N1, hard to approximate, as shown by DE0 ETAL, 2014. As explained in the literature review of section 1.3, highly structured special cases of the click-based MNL model have surfaced in the recent literature. For example, the random consideration electronic copy available at https://ssr set model introduced by Manzini and Mariotti, 2014, and studied by Gallego and Lee, 2017, can be viewed as a limiting case of the click-based MNL where the second stage choice decisions follow a single ranking over the items. 1. In fact, the model of Gallego and Lee, 2017, is a special case of the Markov chain choice model, Blanchett et al. 2016. In contrast, our hardness result of section 2.1 implies that, conditional on the standard complexity assumption P equals NP, it is not possible to represent an instance of the click-based MNL model as an equivalent polynomially sized instance of the Markov chain model. The latter property implies a clear separation between the click-based MNL model in its general form and special cases examined in earlier literature. To summarize, while our modeling approach is related to choice models studied in previous literature, these connections cannot be exploited to efficiently solve the click-based MNL assortment problem. As we proceed to show in this paper, the probabilistic structure of the consideration sets creates fundamental challenges that require new technical insights and algorithmic tools. 1.2 Main contributions. This paper studies the application of the click-based MNL model to assortment optimization, both at a fundamental algorithmic level and in practice. In terms of theory, we tightly characterize the computational status of the resulting assortment optimization problem. We show that this problem is NP-hard even for very basic click-based MNL settings. On the positive side, we develop a polynomial time approximation scheme, PTAS, showing that provably near-optimal assortments can be efficiently computed. This result builds on the development of algorithmic and probabilistic tools to approximate the outcomes of independent Bernoulli trials, representing how customers' clicks generate random consideration sets. We believe that this fundamental contribution may find applications in additional revenue management problems. Beyond our theoretical investigations, we demonstrate the significance of our modeling approach for practitioners. Through a collaboration with the online retailer Alibaba, we have acquired large-scale data sets describing customers' purchase history on mobile platforms, where a customized selection of products is displayed to end users. These data sets come as close as possible to those in use by data science teams in leading retail platforms, scale, feature engineering, data quality, etc. We develop a practical estimation strategy that pieces together the use of clickstream data, machine learning methods, and maximum likelihood estimation. We demonstrate that utilizing the click-based MNL model leads to noticeable improvements over MNL and mixed MNL models in 1. Any instance of the model by Gallego and Lee, 2017, can be efficiently reduced to an instance of click-based term of prediction accuracy, while dramatically reducing the computational cost of the estimation process. In what follows, we present our contributions in greater detail, with pointers to the relevant sections. We conclude by discussing the managerial implications of our work. Hardness results and estimation of choice probabilities. In section 2.1, we show that assortment optimization under the click-based MNL model is NP-hard, by relating the setting to the well-known set partition problem. Our reduction shows that the former problem is intractable even when there is only one item whose inclusion in the consideration set is random, whereas all...
So I'm TAing, right? And a lot of students do not have results because it's like a 2-semester, 1-year program. And it's in the nature of research. Some researchers do not finish in a year. And the thing is that in research you should have positive results. You cannot say but this NP hard, that was actually a nice trick. I hate these problems, but sounds like a positive thing, while it is actually negative. It says, all right, this is a difficult situation, we are not going to solve it. So just saying that it is something NP hard, it's actually a negative result. You didn't come up with a, so that's the thing. Instead of saying we couldn't find a polynomial solution, they say, oh, it belongs to it. I like the marketing of it. It seems smart. Uber CEO, that. Why do you change them so fast? Dictator coming.
Remaining items are deterministically included. That said, as a preliminary indication
Right.
that the click-based MNL model can still be rigorously analyzed, we show in section 2.2 that the expected revenue R, S, of a given assortment S subset symbol N can be efficiently estimated. Specifically, even though the screening phase of this two-stage choice model generates a distribution over exponentially many consideration set CS, we devise a fully polynomial time approximation scheme, FTAS, for computing the choice probabilities pi, is. Approximation scheme. Our main algorithmic contribution comes in the form of a polynomial time approximation.
Okay, why it's useful to prove NP hardness? Why, even though it's a negative result, showing a problem is NP hard is often valuable because justify the use of approximation algorithm, heuristic, or who cares? No, okay, I don't agree with this part. Approximation algorithm, heuristic, or relaxation should stand for itself. If it works, it works. Now, clarifies the computational landscape. We cannot to waste time to looking for. Well, you didn't. Okay, we don't even know P is if P is equal NP, so I don't agree with the second part too. These are all intuitive shit. It often motivates restricted variance. Well, go for the restricted yourself, but add more. So I don't agree. I don't like that.
Scheme, PTAS, for the assortment optimization problem. Formally, for any accuracy level
Became a
number
formula
0,
for people.
our algorithm constructs an assortment whose expected revenue is within a factor of 1 hashtag of optimal, running in O, NO, 1 for log 1, time, as shown in sections 2.3 and 4. At a high level, our algorithmic approach proceeds from a distinction between two regimes of parameters, unlikely items corresponding to low click probabilities, and likely items corresponding to high click probabilities. Our algorithm builds on the intuition that assortment optimization becomes easier to handle when each of these settings is studied independently of the other. For unlikely items, the probability that two items are simultaneously considered is small, and thus, the substitution effects are limited. From an algorithmic standpoint, this means that, in this regime, the assortment problem can be approximately linearized to obtain knapsack-like formulations. In contrast, for likely items, products have non-negligible probabilities of being clicked on. Here, the instance structure is closer in spirit to that of a standard MNL assortment optimization problem, and therefore, we utilize a revenue ordered-like policy. Going from this intuition to a rigorous analysis requires significant technical developments, culminating in enumeration schemes and stochastic inequalities between sums of independent Bernoulli variables using Poisson distributed surrogates, which may be of broader interest. For ease of exposition, we devote section 3.1 to a thorough discussion of our algorithmic approach. Practical implementation. In view of its running time guarantees, our approximation scheme still requires certain enhancements to be readily implemented in practice. Hence, in section 5, we distill these ideas into 3 practical algorithms, ranging from a simple greedy heuristic to an electronic copy available at enhanced version of our PTAS that can also handle cardinality constrained instances. We then conduct an extensive set of numerical experiments in which we test the efficacy of these approaches on randomly generated instances consisting of 20 to 125 products. In this setting, for instances with 40 or fewer products, the optimal assortment can be recovered via a complete enumeration over all feasible assortments. We find that all 3 approaches recommend assortments that are within 1% of optimal on average. However, only the aforementioned greedy heuristic and our PTAS admit practical running times. Concurrently, we examine instances with a number of products ranging from 80 to 125 to show that our PTAS can be employed on instances of practical scale. We observe that our PTAS admits running times that are under a minute on average, even when the algorithm is executed with a small accuracy level, less than or equal to 5%. Case study on Alibaba's data. In section 6, we conduct a case study that focuses on quantifying the value of clickstream data in choice modeling settings. We make use of real historical sales data from Tmall.com, one of Alibaba's largest online marketplaces that connects third-party sellers to customers.
It's not about heterogeneity.
At a high level, customers landing on any particular seller's homepage are often presented with an option to select a discount coupon. Upon clicking on this coupon, the customer is transferred to a coupon subpage that contains 6 products, each of which can be purchased at a discount using the acquired coupon. For the top 10 sellers, traffic-wise, across Tmall.com, our data set consists of all information related to the clicks and purchases of every customer landing on a coupon subpage over a 2-week selling period. Beyond these records, our data set includes a collection of 25 feature values associated with each offered product. We benchmark the click-based MNL model against the standard MNL and mixed MNL models. The latter choice models are estimated via standard maximum likelihood estimation, MLE, methods. Similarly, for the click-based MNL model, the utility parameters of the second stage MNL instance are estimated using standard MLE. On the other hand, the prediction of click probabilities can be cast as a binary classification problem. As such, we leverage generic machine learning algorithms to estimate its click probabilities. Consequently, we measure the fitting accuracy of these models through their respective out-of sample log likelihoods. We ultimately find that the click-based MNL yields 0.5% to 2.5% improvements in fitting accuracy. Given the connection between the mixed MNL and click-based MNL models, see Appendix A, the magnitude of these gains is quite striking, and suggests that click behavior seems to provide a useful signal for the subset of products considered by customers. It is worth observing that the click-based MNL model also has an advantage from a computational standpoint. The estimation of click-based MNL models runs in less than 20 minutes, while the estimation of mixed MNL models exceeds 3 hours. Electronic copy available at https 5.3 results. In this section, we compare the performance of the 3 algorithms described above, by varying the accuracy level #set membership symbol 0.05, 0.04, 0.03. For the remainder of this section, we use PTAS as a shorthand. For the updated approximation scheme, GR for the greedy heuristic, and SAA for the SAA-based integer programming approach. Furthermore, for each algorithm A, set membership symbol PTASGR, SAA, let SA be the assortment returned by algorithm A, and let S be the optimal assortment. We define the R, S, and we drop from our analysis R, S, R, SA. Optimal ID gap of algorithm A for a single instance as all easy instances deemed to be those for which all of the tested approaches recover the optimal assortment. We begin by noting that we were unable to carry out SAA for all problem instances due to prolonged running times for solving SAA-IP, which occurred even when this integer program was formulated with k equals 20 samples. For example, when hashtag equals 0.05, there were test cases for which it took upwards of 25 minutes to solve SAA-IP. Nevertheless, we carried out a smaller set of experiments. To give some insight into the performance of SAA, where we varied n set membership symbol 20, 30, sigma set membership symbol 0.1, 0.5, and beta W, beta C set membership symbol 0.5, 1, 2, and then generated only 10 problem instances for each test case. 6 case study with Alibaba sales data. In this section, we present a case study in which we fit click-based MNL models and mixed MNL models to historical sales and click data from Alibaba, a Chinese online and mobile commerce company that has recently surpassed Walmart as the world's largest retailer, LIM 2016. Our primary goal is to understand and quantify the benefits of using click behavior as a proxy for the set of products considered by each customer. First, we demonstrate that utilizing the click-based MNL model leads to significant improvements over the mixed MNL model in terms of prediction accuracy. Moreover, the computation time needed to fit the click-based MNL is multiple orders of magnitude smaller than the time required to fit the mixed MNL models. Next, we quantify electronic copy available at https://ssrn.com/abstract=33406220. 28. The revenue impact of model misspecification, which occurs when the presumed choice model does not match the model that governs reality. Specifically, we consider the profitability of assortment decisions made under an MNL model, when a click-based MNL model is in fact the ground truth. The assortment instances we consider are generated using the MNL and click-based MNL models that were fit to the Alibaba sales data. All in all, our results indicate that click behavior provides a strong signal for the set of products ultimately considered by customers, and hence, a choice model that incorporates this behavioral premise will likely capture customer purchasing patterns more accurately. Outline. We begin in section 6.1 by presenting the exact retailing setting at Alibaba, as considered in our case study, which is followed by an inclusive summary of the available historical sales data in section 6.2. Then, we describe in section 6.3 and 6.4 the methods employed to fit both the click-based MNL model and the mixed MNL model respectively. The fitting accuracies of these two models are benchmarked against each other as well as a standard MNL model in section 6.5. It is worth noting that we also conduct semi-synthetic experiments to study the cost of model misspecification, where the assortment recommendation of the MNL and click-based MNL models are compared in terms of revenue. To keep the paper concise, these results are presented in the online companion, Appendix EC.4.3. 6.1 General setting. The sales data presented in this section were collected at Tmall.com, one of Alibaba's largest online marketplaces that connects third-party sellers to customers. More specifically, Tmall.com is China's largest third-party business-to-consumer platform for branded goods, such as Nike and Adidas. Throughout this section, the term seller refers to any business that offers its products on the marketplace considered. Customers arriving to the front page of Tmall.com can then navigate to seller-specific pages, which only offer products sold by that particular seller. Upon visiting a particular seller's front page, the customer can acquire a seller-specific coupon by clicking on a coupon icon at the top of that page. Clicking this icon brings the customer to a coupon subpage that contains a personalized display of 6 products, each of which can now be purchased at a discount price. Alibaba selects the 6 products to display with the goal of maximizing the aggregate revenue generated by coupon-claiming customers, as formalized in Appendix EC.4.3. This decision is analogous to an assortment optimization problem. Figure 1 demonstrates how a customer progresses from a seller's front page to the coupon subpage and finally to the 6 displayed products. For each customer,
there was nothing as type or heterogeneity in this paper. Nothing mentioning type. Wow, that was crazy. How do you write heterogeneity? Heterogeneity. Alright, there is no heterogeneity here also. So, okay, I think our problem is not covered by the current literature, but neighboring problems are a lot. And, alright, good for now. Maybe one round of counter. One round, just one. No selfies, just say hi. I'm so healthy and nameless. Wow, it changes so fucking fast. What happened to these clouds? They were all together. It's crazy, Boston is crazy. There were so many dark clouds here, and now it's just separate and lighter. But they went up? No, they didn't even go up.
Let's roll.
Oh shit, that's there. Juta is a sharmuta. Alright. Chill guys, this is a serious thing. Oops, did you love it or no? I could see its shadow. Ah. Oh. Very sure. Why am I so fucking... Ah, fuck. What? This motherfucker. Finally. I... Ooh. How does he kill me? Oh, you're not even looking at the game. Alright, that's perfect. Alright guys. Oh! Let's go, let's go.